Welcome to lecture 11. We have just finished the recovery manager, and for today we will start talking about a different topic in the database technologies, which is the implementation of transactions and how you can actually use the different features in a transaction from the SQL language. This is the module we are currently going to study, the transaction manager. We have finished all the ones that have a green tick beside them, so you should be excited that we are approaching the end of the course. The transaction manager is one of the most sophisticated modules that you can write in software, in any piece of application. It is compatible, for those who are taking the operating system course, to a process scheduler with all its scheduling issues and synchronization between processes and using semaphores and mutexes and so on. So let's start. This is the story. The database engine at any point in time is accepting several SQL statements. All of them are supposed to run at the same time. Every SQL statement goes through the translations we've described early on, reaching to the physical plan, and ultimately the physical plan gets translated to a sequence of reads and writes, and that is put in a container that we have talked about last time. This container is called the transaction, and those transactions are actually running simultaneously under the supervision of the transaction manager, if you like. Now, when a transaction makes a read or a write, which is going to the buffer manager, this read or write actually passes through another component that's within the kind of scope of the transaction manager, or part of the transaction manager, called the scheduler. And the goal of the scheduler is to arrange the reads and writes before actually they arrive to the buffer manager. And this is important because the reads and writes will overlap from all transactions, but not all overlaps are safe or will result in a consistent state, as we will see. So really the brain of the transaction manager is the scheduler. It's the one that schedules how things should run. I mean by things, the sequence of reads and writes coming from different transactions. Now, we have to give due respect to this whole notion of transactions, because when transactions were invented back in 1998 by Jim Gray, it was a major kind of milestone in the history of computer science. In fact, he got the Turing Award for its development. And if you know the Turing Award, well, this is basically the equivalent of the Nobel Prize in computer science. I've put a link to the paper, the original paper that he wrote and for which he got the Turing Award. And by the way, a lot of the stuff we described last lecture when we were talking about recovery and the undo redo logs, and today's lecture builds on transactions. So whatever we discuss when it comes to how the scheduler works, it's really part of how transactions work. So without the scheduler, transactions don't make a lot of sense. So he is basically a major contributor to everything we have discussed last time, and as well we are going to discuss today. So let's put a motivating example. Let's say you have a bank database and you have 3 accounts, A, B, and C. Each one of them has £500. In total, if those 3 accounts belong to the same person, he has in the 3 accounts £1,500. Now, if the owner of these accounts decide to move money between those accounts, the sum should not change. If I take $100 from account, or £100 from account A, and I add it to account C, account A will be 400 and account C will be 600. The total is still 1500. Now, the issue is, what if the person who's doing this is trying to be a little bit smart, and he logs into his account from two different computers, and he tried to transfer money between the accounts so fast to confuse the system? And the question is, will the database engine be confused? Will he end up, if he open multiple terminals, or use multiple laptops or multiple cell phones, will the database engine be confused, and suddenly he now has more money because the database engine did not realize that he is moving money between his accounts too fast to the point that he deceived the database engine? And the answer to the question I'm posing is, actually, it will never happen, so don't try it. The database engine will not be deceived. If you move money between those three accounts, the sum will always be 1500. And the reason why it's the case, because of how transactions work and how the scheduler schedules the reads and writes. So let's develop an example where something like that is actually happening. So I have two transactions, transaction T1 and transaction T2. In transaction T1, I'm transferring 100 from A to B. Obviously, there will be an update statement that does this, but ultimately it will be a sequence of reads and writes like the one you're looking at. We will read A into T, we will take from T 100, and then we will write back T into A. And then we will read B into T, and then add 100, and then write back T into B. Okay? So you take 100 from A, and you add 100 to B. So you start with 500, 500, 500, and you end up with 400, 600, 500. Makes sense, right? So there's really no issue here. Let's look at transaction 2. I will transfer 100 from A to C. So I will read A into S. I will subtract 100 from S. And then I will write S into A, and then read C into S, add 100 to S, and then write back S into C. Okay? So I start with 500, 500, 500, and I ended up with taking 100 from A and adding it to C. So C becomes 600. Now, so I have two transactions. One of them is transferring 100 from A to B, and the other one is transferring 100 from A to C. So if the two transactions run one after the other, well, we don't have an issue. The first one is going to take 100 from A, as you see on the table on the right hand side. So the A becomes the 500 becomes a 400, and then we add that to B. And the next transaction T2, it will take 100 from A. It was 400, now it will become 300, and then we add this 100 to C. So my final result is 300, 600, 600 for the three accounts, and again the total is 1500. So what this should tell you is, if we run transaction one after another, we will never face an issue, because a transaction runs from beginning to end. It starts with a consistent state, ends with a consistent state. We're all happy. The transaction is removed from memory. The next one is introduced. It runs from beginning to end. We're starting with a new consistent state, and we end up with a newer consistent state. So everything is going as we would like it to be going, or as we expect. Now, but we have a problem with the previous way of running things. If we only allow one transaction at a time, that means if we get 100 of them, we are going to queue them, and then we will run one at a time. Even if each transaction takes 50 milliseconds, by the time we reach to the 100th transaction, most likely the user browser has timed out, because the user was waiting, or the user browser was waiting for long enough, and he just timed out. Or maybe if it's not a browser that the user is accessing the system through, if the user is standing by an ATM machine, the user would think that the system is down because he has been waiting for 99 transactions to finish. So to increase the throughput of the system, which is to increase the number of transactions executed per unit of time, what we are going to do is we are going to overlap the transactions. And this is the role of the scheduler, to be fair to all transactions. You see, if you have 100 transactions and you queue them, you are well serving the first one, but you're really being unfair to the 100th one, because the transaction number 100 needs to wait for 99 transactions to finish. And transaction number 99 needs to wait for 98 transactions to finish. Some transactions will be small, some transactions will be much bigger. So if we interleave them, we will increase the throughput because the small ones will finish faster or will finish soon enough. While the long ones, well, ultimately they are already long. It's the fault of the programmer who wrote a SQL that's a page and a half, so they will wait a little bit more. So interleaving transactions or running bits and pieces from every transaction is a very nice idea. And if you have been taking the operating system course, you know about this, that to be fair to all running threads, we will context switch between them and time slice or clock so that every small interval of time is dedicated to a specific thread, which means we take the thread with all its resources and we put it on the CPU, we make it run for a while, even if it's like 50 milliseconds, and then we preempt it and we put another thread, and this is going on all the time, which gives us the illusion that, you know, we are running applications concurrently, which is not really true. As you know, if you're having a single core CPU and you have opened like 5 programs, let's say WinWord, Excel, Chrome browser, and a game you're playing, they are being context switched or switched on the CPU. Everyone is taking a very small duration of time on the CPU, and then it gets preempted and another one is placed on the CPU, and this keeps going on. And you do all this to guarantee that the user experience is not affected, and the user is in the illusion that all the applications are running at the same time. What we're trying to achieve here is the same. We're trying to make sure that all transactions have an opportunity to run. So having said all that, let's look at this overlap. I will start by running T1. So you can imagine that I have a time axis that goes from top to bottom. So I will read A into T, subtract 100 from T, and then write back T into A. Now remember, I already mentioned this at least one time today, and I think also last time, that a transaction runs in its own thread. So a context switch happens. Let's assume this is what's going on. We start by T1 running, and then a context switch happens, and now we're running T2. So we read A into S, we subtract 100, and write back S into A. Now a context switch happened one more time. So we stop running T2, and we go back to run T1. We continue on, reading B into T, adding 100, writing T into B. And since transaction T1 is done, we context switch to T2, and we execute the remainder of T2, which is reading S into C, adding 100, and writing back S into C. Sorry, reading C into S, and then adding 100 and writing back S into C. Now the question is this a good overlap? And here we have to agree on a standard. What do we mean by a good overlap? Well, let's actually look down at the result. The last line is telling us the final values for A, B, and C. I took 100 from A twice, and I added one of them to B and another one to C, so I ended up with the same result we've seen before, 300, 600, 600, which means the total is still 1500. I'm happy because I didn't give the user any free money. He is actually moving money between his accounts, and the movement is correct in terms of the values. Now, this is an important criteria. We are comparing this to what we have seen before, which is running one transaction at a time. Here, we're not running one transaction at a time. We're overlapping them. Almost half of T1, followed by half of T2, followed by the second half of T1, followed by the last half of, or the second half of T2. Now, Let's look at this overlap. Now over here, what I'm going to do is I will start also T1. I will read A into T, subtract 100 from T. But before I have an opportunity to write T into A context switch happens. T2 starts, because the context switch happened from T1 to T2. I mean by context switch that T1 stops running and now we're running T2. So I will read A into S, subtract 100, and write back S into A. Notice that the value of A in transaction T1 and T2 now I'm starting with the same value, which is 500. So in T1, when I said read A into T, I got the 500, put it into T, and then I took away 100, so T is 400, but I didn't have a chance to write that back into A because the context switch happened. And now I start in T2 with A still 500. I will copy the 500 to S, subtract 100, and then write it back. So now I'm writing 400 into A. Now a context switch happens again. The value of T in T1 was a 400, so I wrote back into A also 400. Because when a context switch happens, the value of the temporary variable T was decremented from 500 to 400. So now I write that into A. And then I continue on with the rest of transaction T1, doing the change to B by adding 100 there. And then when transaction T1 finishes, I context switch, or basically, if you would like me to use the appropriate technical term, the operating system realizes that the thread has stopped, the thread for T1, so it preempts it, and then makes a context switch to the one that is still running, which is the thread for T2, and consequently T2 starts running. I will read S into C, add the 100, and then write back the new result for C. Now if you look at the last line on the column on the right, you will notice that there is something weird going on because of what we did, or the location at which we did the context switch. We took a single 100 from A and added 100 to B and added 100 to C. Now you look up at the total and obviously we have a problem now. So if we run such a system, or if we run such an interleaving of transactions, probably the owner of the account will be very happy because we're giving him money for free. He deposits 1500 and then the next day it's 1600. Okay, now obviously we don't want to do this. Here the interleaving is not safe. It's producing an inconsistent result. This should never be a consistent state for the database. So now you understand how important the scheduler is. The scheduler is gonna decide when is a transaction running versus when it should stop. And what it outputs is a sequence of reads and writes that will result in a consistent state. So all transactions are being fed to the scheduler, and the output is a stream of reads and writes that are safe, which means will leave the database in a consistent state. So, to summarize, the database engine scheduler task is to produce interleaving of transaction steps that result in a consistent database state. Now the question is, how do we know which scheduler is correct? If you think of the permutations that are possible here, we could do an interleaving in any number of ways. I could do a context switch, or I could force a context switch in anywhere I'd like by just stopping the thread, and consequently the operating system realized that this thread has stopped, so it will context switch. But the question is, which version or which sequences of reads and writes are correct and which ones are wrong? Okay. So we are going to define what we can describe as a gold standard. And the gold standard for us is what we term, or what is called a serial schedule. So in a serial schedule, one transaction is executed from beginning to end, and then the next one is executed from the beginning to end, and then the next third one is executed from beginning to end, and so on. So there's no overlap, basically, one at a time. And this is our gold standard. because there is no way anything can go wrong here because there's only one running at a time. So this is what you're looking at here is a serial schedule that will leave the database in a consistent state. In this specific serial schedule, T1 runs first, followed by T2. This is another serial schedule where we run T2 followed by T1. This is also valid. It's also a gold standard for us because the final result is always correct. So any one of sequence of runs where we're running one at a time, for us is a gold standard. So if you have only two transactions, then we have two serial schedules, two possibilities, T1 followed by T2 or T2 followed by T1. If we have three transactions, any permutation where each one is running from beginning to end is a serial schedule. It's an acceptable final output. So it could be T1 followed by T2 followed by T3, or T3 followed by T1 followed by T2, or T1 followed by T3 followed by T2, and it goes like this. Any one of them is a good schedule. We don't have really bias here in terms of which one runs first. It doesn't matter. It doesn't matter. Let's say you have two transactions where two users are trying to buy the last cell phone you have of Samsung S20. You only have one copy or one device of Samsung S20. Two users are running at the same time, trying or executing a statement or executing a request, trying to buy that last or only version of the Samsung S20. It doesn't matter which one will actually end up getting the phone. The important thing is you don't sell it twice if you have only one item in the stock. So whether T2 runs first versus T1 or T1 runs first and then next come T2, it's an irrelevant detail. The result will always be the same. In the case of the cell phone example, one of them will get the cell phone, the one who runs first, and the other one will get a message saying that we're out of stock. So the nice thing about serial schedules, that's why they are our gold standard, is that we're running one transaction at a time. So we start with a consistent state S0, and then some transaction T1, when it runs from beginning to end, it will leave us in transaction in consistent state S1, and then the next one runs, it will take us to a consistent state S2, and this goes on forever. And that's why we like serial schedules, because as I mentioned before, there is nothing that could go wrong. It's just one at a time. Now, the correctness actually, we can argue about it even from a theoretical point of view. So let me read this point. It says if any action of transaction T1 precedes any action of T2, then all action of T1 precedes all action of T2. Okay, I'm trying to prove that logically. Okay, so the correctness principle tells us that every serial schedule will preserve consistency of the database state. Okay, now I'm not going to go into a theoretical exercise here trying to prove by contradiction that this will always be the case, but I'm sure you are capable of doing that, so I'm just going to move on. But we have a problem, obviously. What's the issue with serial schedule? Yeah, they're theoretically very interesting, but we cannot run things serially. Running things serially, again, is unfair to transactions who will come later on, because they have to wait a lot till they get executed. And even not necessarily the one who came later on, even the one who arrives at the same time. Like let's say you have 10 transactions arriving at exactly the same instance. The way serial schedules work is that you're going to pick one and queue the rest, which means that the 10th of these guys, you're going to be really unfair to it, and you're just going to have it to wait for 9 of them to finish before you actually start to execute it. So while serial schedules are actually our gold standard, it's not a good idea to run things serially, but we will look to the effect of serial schedules as a guideline to know if what we're doing is correct or not. So it is important from another perspective. It's not that we are going to run things serially, but we will look to the output of a serial schedule, to any one of the serial schedule, as something we need to be sure that we're arriving to or arriving at. And more about this will come soon. So, to summarize, a serial schedule is the gold standard as it guarantees that the database is in a consistent state. However, it's too slow to use since it means running one transaction at a time and thus no support for concurrency or running things in parallel. So what are we going to do? What we actually going to do, we are going to come up with, or the database engine to be exact, it actually comes up with serializable schedules. What is a serializable schedule? Let me read it. It's a schedule is called serializable if its final effect is the same as that of a serial schedule. So as I told you, when we have two transactions, we have two possible serial schedules, T1 followed by T2 or T2 followed by T1. Any interleaving of reads and writes that will produce an output that is exactly like T1 followed by T2 or T2 followed by T1, that interleaving, that schedule, we are going to call it serializable because it produces an output that is similar to one of the serial schedules. Now obviously this gets complicated once you start thinking of 3 or 4 transactions arriving at the same instance, because with 3, as I mentioned, you have T1 followed by T2 followed by T3, you also have T1 followed by T3 followed by T2, you have T1 followed by T1 followed by T3, and it goes like this, okay? So you have many variations or many possibilities. So any output that we come up with that is identical to any one of those variations, we're happy. It's going to be called a serializable schedule and it's safe to run. Okay? Why? Because for the same reason, it will result in a consistent database state. Now, non-serializable schedules, well, it's not always the case that non-serializable schedules are going to result in an inconsistent state, but if you end up in a consistent state, you're just being lucky. Most of the time, you will end up in an inconsistent state. Now, database engines schedulers will ensure always serializability, which means that wherever runs, it is producing the same result as one of the serial schedules. That is a guarantee you get from any decent database engine. So there is an issue with this idea of serializability. If we decide to run serializable schedule where the reads and writes from different transactions are overlapped to guarantee fairness to all transactions, how can we go about it? How can we go about generating such a schedule? Obviously, it is not computationally efficient to scramble the reads and writes and then look at the effect of the reads and writes scrambled on the database engine and then going and evaluate the impact in terms of on the database of all the n factorial serial schedules and see if actually this type of scrambling that we did, or this specific scrambling that we did, matches to any one of the serial schedules effects. And if it's the case, then we accept this schedule as being serializable. There has to be a smarter way to generate a serializable schedule. The schedulers in database engines, what they actually do to solve this problem is that they generate a specific type of serializable schedules. This is called conflict serializable schedules. Now, conflict serializable schedules means that these schedules have been created by considering conflicts only. So we will talk about what do I mean by a conflict, but I want to tell you that this is a special case, but it works great. And this is not the only way we can generate a serializable schedule. There are other ways, but this is one of the most efficient ways, and this is the one discussed in your textbook because it's the most popular way. The idea is to think carefully about steps that if we change their order, the impact of this change will make the result not what we expect, versus steps or reads and writes that we can flip their order or change their order without an impact on the final output. So we have two types of swaps, if you'd like. Swaps of reads and writes that has no impact on the final output, reads and writes from different transactions, and swaps of reads and writes, or writes and writes, or reads, or writes and writes, sorry, that have an impact on the final output. We call the ones that, if we change their order, the final output will change. We'll call them conflicting steps. And the ones that we can swap and the final output is the same will be non-conflicting steps. So let's talk more about this idea. Now, everything I describe here, you have to always keep in mind that the OS is running at a layer below the database engine. The OS is the one responsible for multitasking, for preempting one thread and running the other one, and for context switching. And we have no control on when the context switch happens or when a thread gets preempted. All what we are able to do is to put in the schedule instructions that when a context switch happens and we don't want it to happen at a specific point, we are going to put an instruction that forces the OS to preempt the thread that it just allocated the CPU to and go to another thread. And this will be clearer in a few slides. So I'm always running on the top of OS, and this is something to keep always in mind. So here I have another example of two transactions, somewhat similar to what we have seen before, except there are more operations here. So transaction T1, I'm reading A, subtracting 50 from A, and writing A back. And then I'm reading B, adding 50 to the B, and writing B back. So basically I took 50 from A and added it to B. Now, transaction 2, I'm reading A, finding out what's 10% of A, that's by multiplying it by 0.1, subtracting that 10% from A. So A now has decreased its value by 10%, and I'm writing A back. Then I read B, and I add the 10% of A to B. So if you look at before and after scenarios that are displayed at the bottom of the screen, I start with A 100 and B 50, and if T1 runs first, if according to the way things are displayed on the screen, it looks like T1 is going to run first. It's going to run completely. So I will take a 50 from it, so it becomes, instead of 100, becomes 50, and I'm going to add this 50 to B. So if B starts with 50, it becomes 100. And then when T2 runs, I'm going to calculate what's 10% of 50, which is 5. I will subtract it from A. So A, instead of being 50, now becomes 45. And then I will add those 5 to B, so B becomes 105. Notice that this is a serial schedule where T1 followed by T2 is the plan of running things. And consequently, this is again a gold standard. And what you see at the bottom displayed before and after, before this is an old consistent state A100 B50, and after this is a new consistent state A45 and B105. Now let's look at this interleaving. Again, similar exercise to what we have seen before. I read A, subtract 50, write A back, and then a context switch happens. I read A, calculate the 10%, subtract it from A, write A back, a context switch happens again back to T1, I read B, add a 50, and write B, context switch happen one more time, I read B, add the 10% to B, and then write B to the disk. Now, the after is the same as what we have seen before. So this is an example of a serializable schedule, since it produces an output that is the same as running T1 followed by T2. So this is a serializable schedule. In terms of the stream of reads and writes that will be produced by the scheduler, it's going to be like this. It's going to be read A, do the computation, write A, read A in T1, do the computation, write A, read B in T1, add the 50, write B, read B in T2, add the 10% and write B. So we can actually get a nice interleaving of T1 and T2. This is a serializable schedule because it's equivalent to the serial we presented already. Now, these two are the same. As you see, they are producing the same result. This is what I have been describing already. Let's compare this one to this one. As you see here, the context switch is happening in a different place. I start by T1, I read A, subtract the 50, write A back, and a context switch happens, I read A, calculate the 10%, subtract the 10% from A context switch happens, I read B, context switch happens, I write A, because now I'm running T2, context switch happens again, I add a 50 to B, write B, context switch happens one more time, I read B, context switch now to T2, I read B, and I execute B equal to B plus temp, and then I write B. Now what you're looking at the right side is another serializable schedule. And it produces the same effect as, again, a serial schedule, the one we were looking at earlier. So both of these guys are really nice schedules. They are, even the one on the right, I would argue, it's even more fair because it keeps going back and forth between T1 and T2. So if one of them happens to be shorter than the other, the chance is that, that shorter one will finish faster, which is more fair. So both of them are really nice. Now, the reason why they are really nice and behaving as expect, because the location where, or the instance of time where the context switch happened back and forth between T1 and T2 did not cause us any problems. For example, if you look at the right hand side, we were working with A in T2 by figuring out what's 10% of A, and then a context switch happened. But what we were doing next is that we were reading B, which is completely unrelated to what we were doing in T2. And then when a context switch happened again, we are now writing A, which is completely unrelated to what we are doing in T1. So what this means is that there are overlaps that are safe. And these are, what you're looking at are examples of safe overlaps. Because whatever you're going to do next after the context switch, after you go to the other transaction, is not related to what you were doing in the first one. Not related here means it's not the same element, it's not the same A. You're not doing here A and A, you're doing B and A. So they are different. So you shouldn't be concerned that since you didn't get a chance to do the write A in T2 and the context switch happened, something is going to go wrong, because when you context switch to T1, you read B, which is okay. Well, I was just about to write A and now you want me to read B, that's fine, okay? And then if you look to the continuation of T1, we're not doing anything with A later on. We're just working on the B. Okay, so there are some overlaps. It's okay because what we're doing next, after the context switch, is not related to what we were doing before in the previous transaction that we were working with. And this is the idea of conflicting steps. Now let's look at this one. The one example on the left is the same that we have been looking at before. But if you look at the right, we are now doing context switches at different locations of the code. I start with T1, I read A, I subtract the 50, and then write A. And then a context switch happens, I start running T2, I read A, subtract the 10%, take the 10% out from A, and then write A. And then now you start to seeing the problem. I will context switch, or the operating system will context switch the thread, or preempt the thread, the T2 thread, and put the T1 thread on the CPU. So now I'm running T1, I read B, I add a 50, and I'm just about to write this 50 added to B. When a context switch happens, now I'm running T2 again, and I read B. Okay? Now, a context switch happens after reading B, and I write now the new B. in T1, and the context switch happens one more time, and I do the B equal to B plus temp and then write B. Now if you look at the bottom there, on the bottom right of the screen, you can see that the after effect of running this specific schedule is 45 and 55. A is 45, which is what we expect, but B is not 105, it's 55. So the problem that we are seeing here is that when we started to work with B in T1, when we said read B, B equal to B plus 50, we didn't have a chance to actually write the new B. So when T2 started to work, when the context switch happens, it was reading the old B, not the new B. Which, if you look at the schedule on the right, on the left-hand side, you can see the way at the left, it says read B, B equal to B plus 50, write B, and then the context switch happens. This now we go to T2, read B, B equal to B plus temp, and then write B. I will have it marked here. So you see, this is all happening, the read B, after this write on the left. So I'm reading the new value of B. We didn't have a chance to do that on the right hand side because the context switch happened a little bit early on than what we wanted. So the scheduler, the schedule that you're seeing on the right hand side here is not serializable because there is no serial schedule that will give you 45 and 55. And this is really an inconsistent state in the database. Now, here is another variation, okay, of a schedule. And let's just quickly glance at the bottom right, and you can see that the output is 45 and 105. So, okay, I'm happy. This is actually a good interleaving. If you look why it's a good interleaving, because the context switch happened after B equal to B plus 50 to enable me, or consequently I will do in T2 write A, and then a context switch happens again to write B, and then a context switch happens again to read B in T2, but then I'm reading now the new value of B, so everything works as expected. Okay. So to summarize, a conflict serializable schedule produces the same result as one of the serial schedules. It is constructed by considering non-conflicting steps. And we will see what that means shortly. So to understand this notion of conflicting steps, I'm going to introduce a notation just to speed up the writing of the steps of reads and writes. So R Tx means transaction T reads X. WTX means transaction T is writing X. Now here, and this will be the surprising part to you, is that X varies from one database engine to another. So X could be an attribute of a tuple, like a specific record. It could be a tuple or a row. It could be a page that the tuple is in. It could be even a relation. So we will go around this concept and we'll come back to it shortly when we introduce the notion of conflict serializable steps. Because this will become an issue actually later on, that some database engines, when they write, they don't write a tuple, they don't write a record or an attribute, they write a page, and that's how they write things. So it will affect us, but later on. So just stay on with me till we reach there. So what are the non-conflicting steps? Remember, non-conflicting steps are the ones actually that we're going to play with. This is the ones that we are going to manipulate to generate a schedule that's fair, that also is equivalent to a serial schedule. So there are three non-conflicting steps. Transaction I read X and transaction I read Y. Okay, so you're reading age and you're reading address in the same transaction. Whether you read the address first or the age first, it doesn't matter. Okay, so in terms of logic, you shouldn't have a problem with swapping the reads. If you're reading rows. You're reading the first row and then you're reading the 97th row. It doesn't matter whether you read the 97th row first and next the first row. Okay, again, the reading here, swapping or changing the order of reads shouldn't be a problem. Now, the second one is read and write of different database elements. Transaction I is reading X. Some transaction is reading the age of a specific user. Another transaction J is writing the address of the same user or of another user. Now, who cares? Okay, we are doing completely unrelated things. One is reading age and the other one is writing address. So there shouldn't be a problem. If you make J run first, then you write the address first, and then the I will read the age. If you make I run first, then you will read the age first, and then J will write the address. They're not related in any way. Now, the third one is two writes of different database elements. Transaction I is writing X, say age, and transaction J is writing postal code. So whether you write the postal code first or the age, it doesn't matter. So you can swap these two guys and put J first and then I next, and the result is going to be the same. Now let's look at conflicting steps. Well, two actions of the same transactions. Let's look at the specific actions. Transaction I is reading X, and then transaction I writes Y. Why there is an issue here? Well, it could be that transaction X needs the value of X to compute a value for Y. So for example, if X is the price of a cell phone and Y is the amount of money it's going to charge against the user credit card, it cannot figure out the amount of money it's going to charge to the user credit card after adding shipping. So let's say that the phone costs £15,000 and the shipping is £200. So it needs to know that the price is £15,000, and that's a read. And then it will add the shipping cost and write 15,200, which is the value for Y. So you cannot swap two actions of the same transaction where there is an implicit order of things. Now, it might not be the case, but we don't know. So the general rule is if transaction I is reading X followed by transaction I writing W, we will keep it as is because it's coming from the logic of the transaction as steps like that. The second point is two writes of the same database element. Two different transactions are trying to write the same value, the same record. So for example, one transaction, the user issued it to buy a cell phone. So he's going to pay £15,000. So now he owns the e-commerce website £15,000. And then he decides also to buy gloves for £500. So you're going to add this to that to write the final amount, which is 15,500. So the order of the writes is important. Okay, you are going to update it once and then you're going to update it a second time. If you change the order, you will end up with a different number. So you cannot change the order of writing of two different transactions of the same value. And if you do, you are for sure changing the final result. So it is a conflicting step in that sense that there will be a conflict in the final output. It's not going to be comparable to necessarily one of the serial schedules. Now the third point is in read and write of the same database element. So transaction I is reading X and transaction J is writing X. So if you allow I to run first, then you're reading the old value of X. And then J will write the new value of X. If you reverse them, J will write the new value for X, and now I, when it runs, it will read the new value of X, not the old value. So the impact of that on the logic and on the computations will differ, because if you run I second, it's always working with the new value. So what was probably allowed before might not be allowed now because, say, the user credit card exceeded the limit, say. So the result will change if you actually swap the order. So all these steps are examples of what we call conflicting steps. And what we're going to do is we're going to respect them. So when we see them in the schedule, we don't change them. Okay, we keep them as they are. While we can play with non-conflicting steps, we can swap them. So we come to exactly how the scheduler will generate the schedule. Okay, but to do that, we have to understand this notion of conflict equivalent schedules. Now, let me read it. It says, if S can be transformed into S bar, where S and S bar are schedules, through a series of swaps, S and S bar are called conflict equivalent. Okay, which means both of them respect the conflict that exists within. Now, conflict equivalent guarantees the same final effect on the database, which means that if you respect the conflict, you're not going to change the final results. Now, a schedule S is conflict serializable if it is conflict equivalent to a serial schedule. Okay, so let's try to explain this. What this means is that any serial schedule has some conflicts in it. If you run T1 followed by T2, this goes back to the definition, the theoretical definition, then I'm going to run all of T1 followed by all of T2. So I'm respecting the conflicts between T1 and T2. And I decided to do it this way, T1 followed by T2. Now, any serializable schedule that would respect the conflict due to the conflicting steps between T1 and T2 is conflict serializable to the serial schedule T1 followed by T2. Let me rephrase it. Any conflict serializable schedule that would respect the conflict that exists because we decided to run T2 followed by T1 in a serial manner is conflict serializable to that specific schedule, which is T2 followed by T1. Okay, so we are basically not changing the final result. That's what this really boils down to be. We're not changing the final result. We are keeping it as is. Okay, so as if we're actually running a serial schedule, but actually it is a specific one serial schedule that we are running. Now, the news is all commercial database engines, all really, database engines that you can buy using decent amount of money are supporting conflict serializable schedules because it's the fastest way to generate a schedule. Okay? Now, how do they actually generate this? We will see. It's going to be all about swapping non-conflicting steps. Okay? So, how do I test, before I show you how to generate one, how do I test, given a schedule, that it is conflict serializable? It's conflict equivalent, which means it's conflict equivalent to a serial schedule. Okay? This is what we're going to do. Now, let me tell you why actually we're doing this in the first place. You see, transactions keep arriving to the database engine. And as they keep arriving to the database engine is not supposed to stop them from executing because it's trying to figure out whether the current schedule is conflict serializable or not. So it keeps accepting new sequels as they arrive. It puts each one of them in a transaction and starts it. And then the transaction starts emitting reads and writes, which arrive to the scheduler. And now the scheduler task is to figure out how should it interleave these reads and writes with the other existing reads and writes. Now it turns out actually there is a very nice and simple trick we can do to figure out if a specific interleaving is valid or not. What we are going to do is that we are going to construct a graph and find out if there is a cycle in the graph. And if there is a cycle, we will decide that it is not conflict serializable. And consequently, the current arrangements of reads and writes should be changed by the scheduler. This is how the scheduler would actually do it. Okay? And finding cycles in a graph obviously is not a very trivial task, but it can be done in an O of n plus e, where n is the number of vertices and e is the number of edges in the graph. Okay? If there is no cycles, we are extremely happy, or maybe the scheduler will be extremely happy, and it will allow the new transactions to run given the swaps it has already made to guarantee some level of fairness to the reads and writes. So I have here like a crash course in few slides reminding you with graphs Graph is a very popular data structure. It's, as it's often described, following Saddam Hussein's, analogy, it's the mother of all data structures, because you could specialize it to make any other data structure, and it's usually very entertaining to work with graphs because of how difficult, and mentally challenging they are. Okay, so what we have is a general set of, or a generic way of putting values where we can have connections between any two values, and we call the place that stores the values typically nodes, and the connection between the nodes, we call them edges. Okay, now this is what I was just describing 2 slides ago, that as transactions arrive, the scheduler task is to figure out, after it has already started running a number of transactions, now it gets a new one. Now the question is it safe to just append this new transaction reads and writes to the existing running reads and writes, or existing outputs of reads and writes, and do some swaps, which we are going to describe shortly, and run or not? Because maybe when it just appends this new transaction and do the swaps that it usually does, there is a problem now that it's not a conflict serializable schedule anymore, or a conflict equivalent schedule anymore. So it keeps constructing this graph as transactions arrive, and look for cycles to make sure that it is conflict serializable. So we go back to this notion of graphs. If you remember from your theory course, we have 2 types of graphs: undirected graphs and directed graphs. What we're talking about here is a directed graph, which means that the edge is taking you from one node to another, but it's not the other way around. So if I can go from one node following an edge, the edge is directed, it has a direction. And these are nodes, as I mentioned before, and we're going to call these guys the edges, if you remember from your theory course. Now, when we talked about a cycle means I will start at some node, and then I will after a while come back to that same node. So this is a cycle. If you start from any node, you follow these red arrows, you're going to go back to that node that you started from. This is what we will try to check for, that it doesn't exist in our graph. This is obviously not a cycle, as you see from the direction of the arrows. It looks like it's a cycle, but if you actually look carefully, it's not. You cannot really go back to where you start. Okay? Now, so an acyclic graph is a graph with no cycles. This is an example of an acyclic graph, and our goal will be to check that we are actually looking at an acyclic graph when we build the sequence of reads and writes. So what we are going to do, we are going to construct what's called a precedence graph. Now, precedence here is referring to the order of things. So if I say that T of I, or transaction I, should come before transaction J, then I'm setting precedence. I first, then J. Now, if I'm saying I first, then J, so I will put an arrow or an edge from I to J. Okay? So this implies there is an action of Ti, or transaction I, that occurs before a conflicting action of transaction J. So the way this works is that we are going to look to a schedule and find out the conflicting steps. And when we see a conflicting step, we know that we cannot change its order. We are going to write down the order that is implied from the conflicting steps, and that will be an edge. So I have written down on the right side, as you see, the conflicting steps. And here's an example schedule. The question now that is posed is this conflict equivalent to some serial schedule? To answer this question, we will create a precedence graph. To construct the precedence graph, we have to scan this schedule for conflicting steps. So if you look at these guys at the bottom right, you're going to try to find out where are they. So I can point you now to one. This is transaction 2 reading A, transaction 3 writing A. If you look at the conflicting steps at the bottom right, I am looking for two different transactions reading and writing the same element. So this is going to be the third conflicting step, which says R sub I, or transaction I, read X, and transaction J, write X. Now, the transactions are numbered, so this is a conflict that I have highlighted in green. Now, the conflict needs to be respected. Respecting it means keeping the order of things. What this is assuming that 2 will run before 3. So I am going to put an arrow that 2 needs to run first and then 3. Now I'll go back because I have really here 3 transactions, 1, 2, and 3, and I'll check if there is any other conflict. And I can easily find this one, that transaction 2 writes A and transaction 3 writes A. This is the second conflicting rule, which is if you look at the blue box at the bottom right, this is the second line. Transaction I write X, transaction J write X. So again, this confirms what I already found, that 2 must be running before 3. Or in other words, we're talking here really about being equivalent to be more accurate, we're being equivalent to some serial schedule where 2 comes and then 3 is executed after it. This looks like this is conflict equivalent to one of those guys where 2 comes before 3. Now we keep looking at the conflict steps, and I will find this one, which is transaction 1 reads B, transaction 2 writes B. This is the third conflicting step in the blue box. 2 different transactions, one is reading an element and another one is writing the same element. So there is a conflict here again here. So what this means is 1 comes before 2. I have to respect this order to get the output that is equivalent to some serial schedule where 1 is before 2 and 2 is before 3. Okay? Now we keep looking and there is nothing else. Since I didn't find a cycle, the schedule we were just looking at in the previous slide is great. It's actually a conflict serializable. Let me actually be more accurate. It's conflict equivalent serializable schedule, and it is equivalent to T1 followed by T2 followed by T3. The final output on the